and we're going to take tank 1. Okay, and one thing I want to mention before we kind of go into this analysis is that this is going to be a simple part analysis because we are in a part window. We are not going to be doing an assembly analysis or simulation essentially. And later on you're going to want to do an assembly analysis of this tank in parts. Essentially what you're going to want to do is, or what I've done in the past that have worked pretty well, is that I'll go in here in my configurations menu and I would add configurations or essentially make parts of each of these tanks. So I would cut out everything except this top end cap and name that configuration top end cap. Do that with the middle, so cut out the top end cap, cut off the bottom end cap, name it tank middle, and do the same with the bottom, and then I'd have a top end cap, middle section, and a bottom end cap. And then that way when you go into an assembly you can create an assembly and add welds in between each part, mimicking how it would be in real life and how we would actually assemble it, and then you'd actually be able to see how that assembly would hold up. Because you'll see is that parts, singular parts that are all together, will usually last or withstand more force than an assembly will. So keep that in mind, but usually a part is a really good way to get started and kind of get a general idea. And since what we want to do is essentially determine thickness of the wall for a certain amount of pressure, this should be fine. And I'll show you guys later on an assembly FEA of this kind of stuff, especially once we get into adding the flanges and the piping. From there we'll be able to see much more about how to run FEA for multi-part assemblies. Okay, but for now, let's just go in here, jump in the simulation, new study, and the main difference from this time is, well, nothing really. You're still going to want to do a static study, so you're going to hit static, hit check, and then from here you got your simulation window that is opened up down here. So this is going to be very similar to last time, where you need to input your conditions and things like that. So for our material, we chose 6061 T6, so I'm just going to go ahead and double check, make sure that's applied. It is applied, so we're good to go. Connections. Connections is again really only relevant for assemblies, but if you want, you can always contact the visualization plot. Yeah, but it's only one part, so I'm actually curious as to what it will tell me. Yeah, it doesn't tell you anything. But essentially what that does is contact visualization plot is really useful for assemblies because it'll tell you what's actually touching and what's not. And you can set certain overlapping, and if things aren't touching by like literally millimeters or micrometers, you can say that those are touching. You can give it special inputs, which is really nice. But for connections, we don't really have to worry about external loads. We're actually going to be looking into pressure. So what you're going to want to do is right-click on your external loads, hit pressure, and then what you're going to want to do is select the inside surface of these tanks. So you can do that by doing a split view right here, by going into the model, splitting it, and then selecting the inside faces. Otherwise, you can hover over a surface, right-click on it, hit select other, and then now as you can see, this is the outer surface and this is the inner surface. So now I'm selecting the inner surface, and I'm going to do the same for all of these. And then normal to selected face, because the pressure is acting everywhere. So essentially how these lines are acting is, if you look at the red arrows, it's going to be that same exact way, but on the inside of the tank acting this way. And I'll show you that. And we're going to be doing 20 bar, which is 2 MPa. Yeah, 20, and then we're going to do, so check. And now to double check if we want to see those load lines, we can go ahead and do a section view. Yeah, so now you can see those arrows they're acting along the inside surface of the tank right here, and that's exactly what we want. So one thing to mention before we get started is that your tank, especially a tank like this, your areas of failure are either going to be mainly going to be your longitudinal area, this cylindrical section, and it's going to fail either this way, or a lot of the times you'll see some major stress concentrations around these holes, especially this guy right here. I believe this is usually where your maximum is, so keep that in mind. And if we get huge pressure spikes or stress spikes right around here, then we might have to do some fillets or edit some of the conditions of the analysis to fix that essentially. But okay, going on from there, let's go ahead and add the fixtures. So fixtures is essentially how your tank is going to be mounted. And ideally what would happen is that if this was a flight tank and we're looking at it like the body of the rocket, ideally there would be another cylindrical section like this that gets welded to the bottom of this tank, so it would essentially be held radially right along this surface right here. But since I don't have a model ready for that yet, and that's something we're going to have to explore in the assembly, because you're going to have to add another part here, define a connection set between these two, then apply all the forces and see what happens. I'm just going to simplify the case a lot for right now, and I'm just going to say the bottom is fixed and the top is fixed, because essentially these parts will be welded to other sections of the vehicle, and well, they're going to be fixed in the context of the tank essentially. So we're just going to say those two planes or those two areas are fixed. And you can even, actually, you know what, let's go ahead and I'm going to change that actually. Instead of doing the entire surface, I'm going to go ahead and I'm going to click, I'm just going to select this line. Because essentially what we would have is we would have a thin surface that gets welded to the tank dome right here. So I guess kind of mimicking that is right on the seam right there. Alright, so now let's go ahead and mesh. This is where you're just going to have to play around, but usually curvature base is going to work really well, and you might even need to have the sometimes you might even want the software itself to calculate minimum element size. So what you can do is, especially in larger assemblies, if your meshes keep failing, go over here, blended, curvature based, and then click on the calculate minimum element size, and it'll tell you a really good estimate of what you should input for here and here. But for now, I mean, since this is a pretty simple part, we're just going to go curvature based model, and I'm going to go relatively fine, and this should work no problem. Keyword is should. Okay, yeah, we're good. And I might even want to go a little thinner than this, because these element sizes are actually kind of big. But a lot of the times SolidWorks will tell you if your conditions are within acceptable, because they'll give you like element size, aspect ratio, and things like that. And if it goes above a certain value, it'll actually make the results non-valid. But since it didn't give me any errors, we're just going to go ahead and assume that it's all good. So we're going to go over here to run, right click on the static study or whatever you named it, and just hit run. Now we're just going to wait and see what happens. This should honestly go really quick. Cool. And once again, don't freak out. SolidWorks put an exaggeration factor on this, so to get rid of that, right click on your stress over here and go to edit definition. True scale, yeah, because you can see automatic, it's about, this is about 500 times exaggerated as to what it would be in real life. So just go true scale. It'll give you a more definite idea of what's happening. And I'm going to do the same thing for edit definition for the displacement. And now if I click on this guy, it'll show you if it's secured along the outside of the tank right here. This part will kind of move upwards 0.3 millimeters. So based on the pressure, it's moving the top and bottom end cap just a tiny bit. But if we want to go in here and explore some more of the values, like see what it is on the inside of the tank, because right now we can see is that based on this stress curve, or this the stress displacement, or this stress gradient, stress gradient on the part model right here, we can see that nothing really gets past kind of greenish yellow right here, but the mere fact that the thing goes all the way up to red means that somewhere on the model there is red that goes up to 100 and what is that? 118 MPa. Yeah. So in order to find that, what you're going to want to do is you're going to want to create a split plot, so you can actually see on the inside, because you can't go ahead and use section view. Section view won't change anything, as you can see. It's still a complete part. So in order to go ahead and see on the inside of your part, what you're going to want to do is right click on your result, whatever you want, and you're going to want to section clipping. And then from here you can move this part in and out and explore exactly what you want, but I want it directly half, so I'm just going to go 0, make sure it's right in the middle, and then I'm just going to hit check. Now from here we can get a better idea of where the stress concentrations are, and as you can see, as I mentioned before, it's right along these the holes of where the fluid and the tank connectors are, or the pipes essentially. But if you look over here, you see that they're not getting any more than 118 MPa, which means, we get 118 MPa, and then our yield stress of the material is 275 MPa. So we're way below our yield stress of the material, which is aluminum 6061. So essentially, for a tank at 0.1875 inches thick with a 20 bar, or with 20 bar pressure, we're getting a tank that'll withstand almost twice the amount that we need. So we could probably go up to 40 bar instead of 20 bar, and this tank would still be fine. So what we're probably going to want to do is that since these flight tanks need to be as light as possible, what we're going to need to do is mess around with this thickness and try to find a thickness that gives us a safety factor of 1.5 or 1.25, and it'll be as light as possible. So essentially what we're going to need to do is test a whole bunch of different materials, test some different thicknesses, and come up with the cheapest, the lightest, and the easiest essentially mix of all those three. And that's just going to come from going in here and running these analyses. But as you can see, once you have the model and once you're running it, it's actually pretty easy. So we can go ahead and change the material, so we can explore to see what it was if we chose, say instead of 6063 aluminum, we wanted to look at how a plate steel worked. So we could do a 316 stainless steel sheet. And then in order to do that, we're going to have to rerun everything. But again, shouldn't take too long. And if we go here, we need to load everything. Oh yeah, and this is cool. So this shows you what happens when the pressure gets added. So blue is and so you can see how the stress of the tank acts as it gets put under that pressure. But yeah, as you can see, yield stress went up as we changed the material, but the stress of the tank itself didn't really change, because it's more or less dependent on the geometry is your maximum stress. So and it's still going to be right along that line. But your displacement will change based on your material. So instead of being 0.3 millimeters, it's 0.1, and all that. But yeah, I mean that's essentially kind of very preliminary how you go ahead and make a tank, and then run some analysis on it. There's going to be a lot more that you're going to want to do to make this more accurate. And as I said before, we're going to kind of get into that as we start adding assemblies together, add piping, and start building up the entire vehicle together and then running analysis on it all, because that's going to provide the most accurate case. I'm trying to think if there's a few other useful things I can show you. I think I might make a video one day showing you how to edit all of these aspects of your analysis, because some of this stuff is actually pretty useful. For instance, you can save all of, so if you wanted to export pictures of your tanks, and of like all your displacement, your strain, your stress, you can right click in your results here and go save all plots as JPEG files. It'll save all of them for you instantly, so you don't have to go ahead up here and say file save as and do it that way. Another cool thing is that once you have your tanks done, you can I'll go over that in a different video. That'll be a lengthy thing on its own. So I guess for now, try to mess around with making your own tanks and running some analysis on them, and telling me what you find. Because essentially is that if we do find a certain thickness that'll work at one point, we will need to find the closest matching I guess real world thickness that they make, because they make standardized thicknesses for tubes that we're getting and these elliptical ends that we're getting. So we're gonna have to find out what's gonna be the minimum acceptable one that we can find. But that'll come once all these analyses are done. So for now, just kind of get going on those. And if you have any questions or if you want tank models like this, let me know, and I can get those out to you. But for now, I guess have a good one and good luck on trying to do this for yourself. And I'm going to go ahead and continue making some of these videos explaining some of this, how to edit some of these extra parts of your FEA simulation tabs. But alright, I'm going to call it there. So have a good one, guys. Peace. Alright guys, so before we go ahead and actually end this video, I want to actually mention one more thing that our grad student of the project actually mentioned to me the other day for this video specifically, and that has to do with the whole yield stress versus ultimate tensile stress of the tank itself, and what we can actually still use and what will actually result in a failure, essentially. So to kind of highlight what I'm talking about, I'm going to go ahead and change this 2 MPa to 8, because essentially what I want to do is show a failure. So I'm going to go back into here, rerun the analysis and see what happens. But essentially, okay, cool. So 8 was maybe a little much, but essentially what the point is I'm trying to bring across is, so we have our yield stress of 1.7 of 172 MPa. You know what? I'm going to edit this. So now here we go. These are MPAs. Yeah, so 172 MPa. It's right around here. So anywhere you're seeing this kind of light teal turning into a green color, that means the material is actually yielding. So anywhere down here, in here, up in here as well, and around the holes. But the thing is, that only tells us that the material will be yielding. It doesn't necessarily mean that the tank itself will fail. So if you're going to want to look at this analysis and talk about failure versus non-failure of your design, you're going to want to go to your material and check the ultimate tensile strength. And you're going to want to compare that to the whatever the maximum value you see here. So if we picked a 316 stainless steel sheet, as you can see right here, the tensile strength is 580 MPa, and the maximum on the model is 473. So even though this model technically is saying that it will yield in certain locations, it will not fail. And that's kind of the point I wanted to highlight, is that just because you see this red arrow and it's yielding on this graph and on your model doesn't necessarily mean that the part will fail. Now, when you do something like this, make sure to mention that you are comparing it to the ultimate tensile strength and not the yield strength. But also always mention where it is yielding to the material, and I guess a quick blurb as to why, or what's going on, and why we're kind of going with the ultimate tensile strength instead of yield stress. But essentially, since we want to make these tanks as light as possible, and we don't necessarily, we care if they deform and things like that, but these are most likely going to be minimal use tanks. Like, these are going to be made for flight, and they're going to be filled up maybe once or twice and launched, and that's it. So we're going to have to really determine a minimum thickness that's acceptable, and keeping in mind the ultimate tensile strength versus just the yield stress of the material. So cool. I just wanted to quickly mention that because our grad student mentioned that to me the other day, so I just wanted to quickly jump in and add that. So I guess good luck on your analysis, and let me know if you have any questions. And if you want a tank model like this to run your own analysis on, just let me know, and I'll throw them in the Google Drive probably, so you can just grab them from there. Alright, I'm going to sign off, so see you guys. Peace.